Good afternoon. Hello, everyone. Okay, so we will finish the binary search tree today, and there will be another data structure called disjoint sets, and we will also talk about these data sets as well. And in particular, the disjoint sets will be used again when we introduce graph algorithms from next week. Okay, so today in the slides today, there will be some concepts about a graph and what are the internal elements in a graph. Some of them will be covered today, but just a little bit, and a more systematic introduction will be given from the next week's lectures. All right, and let's pick up some of the previous contents first. Okay, so the binary search tree. Okay, so the most important thing about this data structure is the so-called binary search tree property. Okay, it is an inherent property of this data structure, which is also easy to understand. It's just a way to organize the nodes so that given any node in that tree, and the parent node is always in the middle. Okay, it's greater than any elements, any nodes in the left subtree, and it is smaller than or equal to any nodes in the left subtree, in the right subtree. Okay, so it's a data structure organized in such a way so that the search operation in this data structure is very fast. Okay, so I think we have covered the search algorithm. Yeah, we have talked about this tree search. Okay, so it is actually the key operation, the key query operation that a binary search tree supports. Okay, so basically, this search algorithm utilizes the binary search tree property. Okay, so the key is the comparison here. The key is the comparison here. So the target key is some value that we wish to find in the tree. So we're gonna compare it with any node that we come across during the search. Okay, and then we use this comparison to decide which path to trace down. Okay, right. So if the target's value is smaller than the value of the parent tree, then we need to return the results we need to go to the left subtree, right? Because it is according to the property. If the target value is greater than the parents, then based on the property, we need to go right? Okay. All right. So there are two implementations. So this example of the recursive tree search versus the non-recursive or iterative tree search is also it's just a more advanced example of the binary search. Okay, we in our first assignments we defined the problem of searching an element with certain values within an array. Right, in an array, it's not a tree structure. Okay, but we basically use the same idea. It's like we compare the target value with some of the midpoints. And if it's an array, then it's the midpoint we want to compare. But here in the tree, it is we should start with the root node, okay, and the parent node in the middle kind of serves as the midpoint of comparison. All right, so we also covered the minimum and the maximum operation. Okay, so these two operations, they also the basic query operations on the binary search tree. So these are simple operations, but they will be used later on in other more advanced operations. And the idea is also straightforward, like because we know that. So the idea is that but because we know that the left subtrees is always smaller than the parent node. So if we want to find the minimum key, then we need to always follow the left child pointers, right? We need to trace down towards along the leftmost side, along the leftmost branch, okay, until we hit a point where there's no left child anymore. So that node is the leaf node, which needs to be returned, right? And on the other side, if it's the maximum we want to find, then we simply use the right. We just go down along the right subtree, along the right child pointers. Okay, so that is so much for the review. Let's talk about the remaining parts of the binary search tree today. So I just pause the recording, and I need to play the slide. Here we go. Okay. So we will look at these two concepts. Oh, let me start recording. Resume. So I think the recording is on, right? Okay, so let's look at the successor and the predecessor. So we already seen this in order tree work procedure. Okay, so this in order tree work is a procedure that basically lists all the elements in the tree, right? In an order, right? It will print the left child first, and then print the parents in the middle, and the right child, right subtree on the as the next one, right? So that's printed elements in order will basically result in which basically allow us to define the successor and the predecessors. So in this case, for example, if we call the in order tree work on this tree, it will print 2, 5, 5, 6, 7, 8, okay, in such an order. And we now, if you look at the 5 in the blue circle and the 6 in the orange circle, then they are in such a successor and predecessor relationship. So the 6 is the immediate predecessor. It is a predecessor of 5, and 5 is the successor. Sorry, it should be the opposite. So 6 is the successor because 6 follows 5, and 5 is the predecessor. 5 appears before 6. Okay. So, like, how do we know this? Right? This is something we want to figure out, and obviously it is not that straightforward again, but it's still doable. Okay, so I give the algorithm here. So actually, it's just there are two cases we can look at. Okay, so if you look at the algorithm, there is a if condition. So the first two line, it's an easier case. So it will, given a node, the algorithm will first check whether the right subtree is null or not. So if the X node contains, it has a subtree, it has a right subtree, then the successor of X must exist in the right subtree. Okay, so X is here, all right? So if it has some elements in there, right, that's the right one. So if the right subtree is not empty, then the successor of X must exist in the right subtree. That's for sure, right? Because all the elements that are greater than X or equal to X must exist in the right subtree of it, right? So in that case, we will simply call the minimum function, which we just defined, okay? And this tree minimum function, it essentially will trace down until the leaf node along the right branch, right, within this right subtree. So that is a easier case. And for the other case, then things are trickier. It's like if X don't have such a right subtree, then how do we find the successor? So that is a trickier question we will look at in the next few slides. Okay, so again, so this is the case one, which is the easier case. Okay, the right subtree is not empty. So if you look at the node Y here, okay, so what if we will want to find the successor of this node? Then we can immediately go into the right subtree, which is 7, right? It is the minimum elements in it, which is 7. And we can also find so if it's a different question, if we want to know the successor of Z, for example, right? We need to go into the right subtree, which is these two nodes, and we want to find the minimum among these right subtree, which is 9, right? So in these two cases, it's still pretty much easy problem. So what if a trickier case, say now we want to know the right subtree, we want to know the successor of a node whose right subtree is empty, for example, the node T here, right? There's no right subtree for T. So what we need to do here is that we need to go up because there's no way to go down. But since the node T has a parent, we can go one level up, right? And we need to go up from the current T node until we encounter a node that is the left child of its parent. Okay, so that is a little bit unintuitive, but we can look at this problem. We can look at this through this concrete example. Okay, so in this case, because T doesn't have a right child, so we should go up a level, which means we go to Z, right? So, but now since T is the right child of Z, which doesn't satisfy the requirement, because we want to find we want to find the a node that is the left child of its parents. Okay, so here, if we look at line 3, right, it records the parents of the current node, right? Let it to be y. So in this example, the parent of t is z. So at the beginning, y will be z, right? So the while condition is that the y shouldn't be empty, and the x is the right child of the x is the right child of y. Okay, so if these two conditions satisfied, the while loop will keep running. So if y equals z, then of course the t is the right child of z. Okay, so the while loop will be executed, which means we need to go up again, and by go up again, we need to first record. So let x be y. So y is z. So now the new x will be z. Okay, and y will be one level up, which will be y. Okay, so because the variable names I used is x, y, z, which overlap with the internal variables of the function. So it's a little bit confusing. But if you work on a paper yourself, you can replace this x with a's, b's, c's, right? So that'll make the process easier. Okay. So anyway, if we look at z, then since t is the right child of z, so the while loop doesn't break. It needs to carry on the next iteration. So we will need to go to the node y. But since z is also the right child of y, and the while loop still carries on, okay, so we need to go to x. Okay, so now if you look at the node x, okay, let me use a different color. If we look at the node x, oops. Okay, the node x, since y is the left. Okay, so here's a typo. It should be left. Okay, so the y is the left child of x now, which means the while loop will break. Okay, because the while loop requires it examines the right child relationship. If we find a left child relationship, then that while will terminate. So we need to return y. Okay, which in which case the y being returned is the x node here. Okay, so and that means the x is the next successor of t. Okay. All right. So that is the successor problem or successor procedure. So if we go to predecessor, it's basically a same question, a same problem. Right, we still need to look at two cases. The first case is easier. It's like if the left child is not empty, right? So if you look at the blue node, the two blue nodes, the predecessor of the node 6 here is the node 4. Because the left subtree of node 6 is not empty. Okay, so we basically need to find the maximum elements in this left subtree. Right, it's opposite to the successor case. Right, we want to find the predecessor. Then we need to find the biggest elements in the left subtree. Right, which turns out to be 4. Okay. And the second case is just like the previous slide. If we want to find the predecessor of 17 here, because it doesn't have a left subtree, Okay, so we basically need to go up, right? We need to go up, right? We need to go up and find such a node that it is the left child of its parents, right? It has it is the right child of its parents. Okay, so basically we will go to this node, the root node, and we find that it has a right child here, which is 18, and we will return the elements 15. Okay, so if you flip around the left to right in the previous of the previous procedure, you will get the procedure for finding the predecessor. Okay, so I don't put the code here. All right. Okay, so I think that's pretty much for the query operations on binary search tree. Okay, we have covered the tree search, the maximum, minimum, the successor, and the predecessor, right? So since the queries don't cause any change to the data structure, and then we're gonna look at some operations that will change the states of the data structure of the tree. Okay, so of course, first of all, we will want to know how to insert elements to a tree. Okay, so to insert elements into a binary search tree needs to make sure that the new value need to be put into the appropriate position. We need to find the right position so that the binary search tree doesn't break. Okay, we want to follow the rules so that all the left subtree is smaller than the parents. The parent is smaller than the right subtree. That is the principle we want to hold. Okay, so the algorithm actually looks like this. Okay, so we given a tree, for example, the tree is T, okay, and this tree has some attributes that points to the root node. Okay, so we can indicate a tree like this, and the Z is the new node to be inserted. Okay, and the Z contains the new value here. Okay, so we basically need to first construct a node. Okay, and it has some value, and we should indicate that the left child of Z and the right child of Z, so that this tree can be inserted. Okay, all right, so if we look at the first half of it, right, there's a while loop. Okay, so and we can find that this while loop is very similar to the basically the tree search algorithm, right? We let X to be the roots. Okay, so we will not look at Y first. Okay, we'll just focus on X. So if you look at X, the while loop will not end until we hit some leaf, right? So the while loop will keep running by tracing down the tree from the root. And what we do in this while loop is to choose which way to go, right? We use the if to compare the new value, which is in z.key. We will compare the z.key with the key value of X. Then if the new value is smaller than the current key, then which means we need to go into the left subtree, right? By assigning x.left to X, right? If otherwise, if the new value is greater than the current parent's value, then we need to go right, right? That totally makes sense, right? Because we want to follow the binary search tree property. We don't want to break it. We want to find the correct position to insert the new node. Okay, so these parts is a little bit similar to tree search, right? So we're going to find a simple path downwards, okay, to look for a non-pointer, which is a leaf node, right, to insert z. Okay, so now since we have another variable y, okay, so this y is actually a variable that we use to keep track of x. Okay, so since look at the condition of the while loop is that x doesn't equal null, right? So the while loop will only terminate if we find x to be null, which means either the left child or the right child is empty. Okay, so that means we need to remember the position. We need to remember the previous x before it becomes a null, right? So that's why before the if else, we need to remember the previous position of x using this second pointer or a tracer pointer that remembers the previous position of x. Okay, so when x becomes null, then the y would be the parents, right? Would be the last, would be that leaf node. Okay. Okay. So y will be used after the while loop. Oops. While after the while loop ends. Okay. So if you look at the second half of the algorithm, and these are just regular operations to properly assign the correct values to the pointers. So most importantly is the parent pointer. Okay, since y remembers the correct position of the last x, right? So we will need to let the parent node of z, the parent pointer, points to that correct position. Okay, and if y is null, which means it's still the root node, so we will let the root pointer points to the new node. Okay, and again, the next else if and else decides whether we should assign the new, whether we need to assign the new, insert the new node as a left child or right child by comparing the key values of the new value with the parents. Okay, so these are just standard operations. Okay. So that is the insertion operation. Okay, let's look at an example. Okay, so that you can have this process more clearly demonstrated. Okay, say we start at the root node, right? The x and y's are pointers, or you can think of them as the positions of the nodes. So x first points to the root node that has 12. Okay, so here I use x equals 12 basically means that I let x point to that node. It's not a assignment of the value 12. Okay, just for simplification in this case. So since the node, assume that the node that we want to insert is 13. Okay, so our target value, the z. So the z dot key would be, the z dot key in this case is 13. Okay, so we will compare 13 with 12. And since it's greater than 12, we need to go to the right child, right? Then we will go to this node 18, right? And 18, and also when x becomes 18, then y remembers the previous position of x, which is 12. You see, the y keeps track of the previous position of the x node. Okay, so now 18 is greater than 13. So the next step, we should go to the left subtree, which will give us 15, right? And when x becomes 15, the previous x is copied to y, right? Y remembers the previous position, which is 18. And then 15 is greater than 13, right? And since now x is, if we go to the left child of 15, it's a null, so the while loop will break. All right, so x becomes null here, but y will remember the last position, which is 15. Okay, so the y, you see, the y is useful now because it remembers which parents, where the parent of z is, right? So the parent of z should be 15, which is returned by the y. Okay, so we will let the 15 be the parent of z, and then since 13 is smaller than 15, so we will let 13 be the left child. Okay, so yeah, that's a complete example of tree insert. Okay, so with insertion defined, and then naturally we want to know how to delete nodes from a binary search tree. Okay, so the deletion operation is a little bit more tricky than the insertion. So I think insertion is actually quite easy to follow. We just follow the binary search property to choose to go to left versus right, right? And the deletion case, the deletion operation, is a more complex one. We need to consider 3 cases if we want to delete a node from a binary tree. But again, so among these 3 cases, 2 of them are very simple. Like it's the first 2 cases are really straightforward to understand. Okay, so first, if the node we want to delete has no children, then it is the simplest case, right? We can simply remove it because it's already the leaf node. We can simply remove it out of the tree, right? Because it will not cause additional consequences, right? Because it doesn't have additional other nodes attached to it. And then if z has just 1 child, then what we're gonna do is to elevate that child to take z's position, right? That is also understandable, right? Because if there's only left child or right child, either one, if there's just 1 child, then we can simply replace z with this child, right? So because there's no conflict, we don't need to choose between left child or right child. So these 2 cases are the 2 simpler cases to look at in the deletion, for the deletion operation. Then if there are 2 children, then that is the 3rd condition we want to think more carefully about. Say, now if z has 2 children, we have both left child and right child, then what we need to do is to find the successor of z, which is y, okay? We want to find z's successor, y, okay? And this y, as we have shown when we define the successor procedure, this y must be in z's right subtree, right? We want to find that y, and then we need to have y to take z's position, okay? That also makes sense, right? Because if we think of all the nodes in the tree as if we sorted them in order, just like what we did using the in order tree walk, right? We can define the successor element, successor node for each node. Then since one node is deleted, then naturally the next one, the successor of it needs to take its position, right? But there's more complex pointer relationship we need to figure out, okay? So we will, based on these three cases, and then we will look at the solutions for each, okay? So for example, and straightforward deletes for the root for the leaf node 9 is simply to remove it, right? It's will not cause any consequence. And if it's just 7, if it's just a node with 7 or 13, for example, it's also like easy, right? If it's 17 we want to remove, we will remove it. 13, not 17. If it's 13 we want to remove, we will just let the 9 go up, right, to replace 13's old position. If it's 7 we want to remove, then we will remove it and let 13 go up to replace the position. So the most tricky one is like if we want to delete like 6 or 15, right? So then it will be a little tricky. Okay, so like we want to find the successor of it. So what would be the successor of 6? Okay, it'll be 7, right? We basically want to let 7 to replace 6. And in the case for 15, then we need to find the successor, which is 17 here. Like we want to the 17 to replace it. So it's a little tricky because here this example is okay, but in other cases we will find that what if the 17 also has a right child, right? What if the 7 here is also has more child? So we will look at these more complex scenarios in the next few slides. Okay. All right. So let's try to define this tree delete procedure. Okay. And it takes a tree, right, and a node which we want to delete as inputs. All right, so the first case is that, so here from these slides on, we organize these 3 cases a little bit differently from the 3 cases that we talked about 2 slides ago, but essentially they cover all the cases, all possible cases, okay? But in this way, we will find that the cases will be defined more easily, okay? So the case 1 on this slide, it says, if the node we want to delete has no left child, okay? So if there's only a right child, or the right child could be null, right? So we are actually covering 2 cases. So if the Z has no child, okay, and then we can simply replace Z by its right child. Okay, so as this plot indicates, right, the Z here in the middle is the one we want to delete. And since it has no left child, there's a null here. So we can be bold, right? We can quickly delete Z by replace Z with its right child here. Okay. So this right child can have its own children. It can have its left subtree and right subtree, but that doesn't matter, okay? Because the Z doesn't have a left child, so we can just cross out the Z and elevate the R up, which results in the new tree like this. So now the Q points to R here. Okay, so that is the results of deleting Z in this case. Okay, so in this case one, the Z has no left child. All right, and the case two, it's asymmetric basically. If Z only has left child, right? So this time then the right child is now. Then we will replace Z with its left child. I think it's the symmetric case, okay, which is just easy to understand, right? We will replace the Z, cross them out, right, and elevate L up, so it becomes a new tree like this. Okay, so the third case, okay, is something we will need to spend some time on. So if Z has two children, right, we want to, because Z is deleted, the result of deleting Z is that we want to replace it with Z's successor, okay, which is the natural follower within the node. So we need to find Z's successor Y, okay? And we know that the successor over Y must be in Z's right subtree, right? According to the binary search tree principle, right? All the elements that have greater values must be in Z's right subtree, okay? So we want to find the successor Y within the right subtree. And also this Y should have no left child. So this is something we can think about. So why this is the case, right? Say we have a Z here, right? We have some left subtree, right? We have some left subtree. Right? There could be a lot of elements, okay? Let's say if the Z is here and the Y is here, right? So this is our Y. Say if Y is the successor of Z within Z's right subtree, and then Y should have no left child. That is obvious, okay? So it's like if we let Z has some left child, like this. This is the let Y have some left child. So this is the Y dot left. So the left child must be smaller than Y, right? And then it's also within the right subtree here, which means it's greater than Z, right? Which means the Y dot left is actually the successor, not Y, right? So here's a conflict. So if Y is the successor, then it must have no left child, okay? So that's the case 3. We need to solve these relationships, okay? So what we need to do is we find the successor of Z, and then we splice Y, find the successor and splice it out of its current location. And then we need to again go deep into 2 cases. Let's call them case 3A, okay, and 3B. So the first case, 3A, is that the successor Y is Z's right child. It's the direct right child. Okay, then that'll make things easier. We will, because it's the right child, we will replace the parents with the right child. Okay, we'll just move the right child Y up to replace this position. Okay, so for example, in this case, we will find the Z in the middle and the Y, the successor of Z, Y is here. It's the direct right child of Z, and Y also don't have left child, right? So in this case, we will simply replace the Z with Y, okay? And the second case is the most complex case. It's like, case 3b, it's like, okay, the successor is indeed within the z's right subtree. Okay, but it is not. It is not the z's direct right child. It is somewhere deeper. Okay, so what we're gonna do is 2 additional steps. Okay, it's because it's deeper, then we need to basically first replace y by the y's right child. Okay, because we will take y out, so we will first take care of y's child. We will replace y with its own right child, and then we take the y out and then replace z with y. Okay, so that comes with additional step. Okay, so in this plot here, the z is in the middle. We want to delete it, and we find the z successor y in its right subtree, right? So since y is deeper down there, it is not the direct right child of z. So before we splice y out and replace z, we need to take care of y's child, right? We shouldn't leave the y's child without taking care of it. Okay, so we will first replace y by its own right child. Okay, so the right child of y is here. The y's right child is here, starts with x, right? So we need to move these subtree up to replace y's position. So now the x connects to r, right? So the r directly connects to x now, right? Well, this is not direct connect, but I mean, use this x to replace r, right? And then the y will be elevated, okay, to replace the position for z here. Y will becomes here. So the next step is to put the whole subtree here to replace the z here, right? So the z is gone and the y is replacing the positions for the original position of z. Okay, so that is the trickiest case for deleting a node in a binary search tree. Okay, all right. So because in this we haven't defined the procedures clearly, concretely, right? So we will need some helper procedures because we have talked about moving subtrees around, right? We want to move y by its own right child. We want to replace z by y. So all these operations actually require some auxiliary procedures that can handle the pointer relationships properly. Okay, so for that purpose, we will first figure out how to move subtrees around in the tree. Okay, so we will define the so-called transplant procedure. Okay, so the goal is the purpose of it is to replace one subtree with another. Okay, it's a pretty general procedure. Okay, so it looks like it takes inputs 2 nodes. Okay, the function is to replace the subtree rooted at one node u with the subtree rooted at another node v. Okay, so that the u's parent becomes v's parents, and v is now the new child of u's parents. Okay, so this transplant looks like this. Okay, and it's just a if else consists of several if else statements. Okay, so it's basically by comparing by looking at whether the U is the left child of its parents or the right child of its parents. Okay, so if U is the right child of its parents, then we will assign the V to be the new child to U's parents, right? Otherwise we're gonna let V be the new right child. Okay, and we will also replace the parent child of V properly. Okay, so this transplant is quite like I would say it's straightforward to understand. Okay. All right. So that's the transplant, which will be necessary for defining the tree deletes. Okay. So now we have transplants, which means we can easily move trees around. Now let's go back to the 3 cases for the tree deletes. Okay. So again, let's look at the procedure. In case 1 and 2, in which the node to be deleted only has one child, either left or right, right? So the first part of the procedure would be just for handling the first two cases. Okay, if there's only the right child, right? If Z only have right child, then what we're gonna do is to transplant Z by transplant the right subtree to Z, right? So this solves the move around operation, okay, implements the move around operation. And if the Z only has a left child, then we will replace Z with its left subtree, right? And the last operation, the last case, right? If the node Z has 2 children, right? So that's the complex case in which we want to find the successor, right? We want to find the successor of the tree. So, right? Remember, how do we find the successor of a tree, of a node, right? So here we will find the successor of Z by going to the right subtree, right? We find the minimum element within the right subtree of Z, which is the successor, right, of Z. So we let it to be Y. Okay. So next we will have a if statement. Okay. So this if statement handles the more complex case, which is case 3b. So it checks whether the parents of Y, the successor, is Z or not. So if the parent of Y is Z, which means the Y is the direct right child of Z, which is easier. Okay, so if not, we're gonna replace Y by its own right child. Remember that, right? We will call transplants by replace Y with its own right child. Okay, so and we will move Y up. Okay, by assigning the right child of the new Y to be the right child of so we'll assign the right child of Z to be the right child of Y, and we will let the parents of these child node points to Y. So we are basically isolating the Z, okay, because we want to replace Z with Y. Okay, so the next step is to replace Z with Y by calling these transplants procedure, right? We replace Z with Y, and then we need to take care of the left subtree properly, okay? Because Y is replacing Z now, and if Z has some left, which is on the left side, which is irrelevant in this case, but we still need to take care of it, right? So we need to assign the left part to the Y dot lefts, and also let it point to Y properly. Okay, so that's the implementation for the tree deletes procedure in a complete example. Okay, so a little bit analysis of the running time. So because if we go back to the transplants, it's actually a quite easy implementation. I mean, it's not a no loop in it, right? So the transplant is just if else. It's a constant running time algorithm, right? So the tree delete, if we look at all the code here, there's a transplant plus transplant, and the other constant running time statements. So we just need to focus on this part, right? The tree minimum, right? Other parts are all constant running time. So the only part is the tree minimum, and we know that the tree minimum is to trace down the right path, the right subtree, the left subtree, right? The left subtree. We just trace down the tree in such a way it goes to the left. So, but that's this algorithm has a while loop in it, right? So it is not constant amount of time. So it actually depends on the height of the tree. Okay. Usually speaking, the height of a tree. If the tree is a balanced one, it's in a pretty balanced shape, then we can say that the height is proportionate to the logarithm of n, just like a heap, right? Remember when we build a heap data structure, basically the heap operations is proportionate to logarithm of n. So it's a similar case in here. We will have this tree delete operation runs in big O of h, and h is basically the height of the tree. Okay. So yeah, so that's all we have for the binary search tree. Okay. So we will have some time to cover the disjoint sets. Okay, so I think it's just a few slides, okay, but I want to introduce the concepts. That is the main purpose for these few slides. We're gonna see it later again in the advanced graph algorithms, but I think it will be helpful if we look at the definitions first. So as the name indicates, a disjoint sets, right? It's a data structure that deals with sets. Okay, it basically maintains a collection of sets. So this collection here, S1, S2, Sk. So these each are a set. Okay, the S is for sets. So S1 is a set. S1 has its own elements, and S2 has its own elements. So the collection of all the sets together is a joint set. Okay, so the joint name, the joint means that if the two sets are joined, then they have disjoint. If they are disjoint, then they have no elements in common, right? So the union, I mean the intersection between the two sets are empty or none, right? So that is basically what the joint mean, disjoint mean. Okay. So in implementation details, we will identify each set using a representative, which is one element in that set, okay, which is some member within a set. It could be randomly chosen, or it could be chosen by some predefined rules. Okay, so yeah, chapter 21 will have more detailed introduction to this data structure. Okay, so the common operations supported on the disjoint sets includes the make set operation, which means it will create a new set whose only member, okay, or which means the only representative is X. So X is an element. Okay, we will provide one element and create a new set that has only just that element in it. Okay, so this is something we will use. And the union is a common operation between two sets, right? It's like we will unite the sets that contain X and Y, okay, into a new set. Okay? So the argument provided X and Y, the lowercase x and lowercase y, they are not sets, but they are the representative of a set. So X represents the element that contains the element X, and Y represents the set that contains it. Say they are Sx and the Sy. So the result of union is to combine these two sets represented by X and Y. Okay. Right. So the example here is that if X contains these three elements and the Y contains these three elements, and the union of these two would be a new set that has 6 elements in it. So you see the property here, the Sx and Sy here, they don't have intersections, they are disjoints. Okay, so this is a characteristic of the disjoint set data structure. So the union of these two is just the summation. It's just we just include everything into one set, into one curly brackets, right? All right. And the last one is find set X. So it returns the representative of the unique set that contains the element X. Okay, so it's like, for example, we want to know the set of W, okay? And since W is not the representative in this case, and find sets on W will return the element X, because the X is the representative of the set Sx. Okay, so these are just the helper functions that will be useful in the future. So in the next 2 slides, there will be some concepts in the graph algorithms. So it's okay that we don't know about it, but I'm gonna run through these 2 slides just for a preparation for the future lectures about graph algorithms. Okay, so there's a term about the connected components in an undirected graph. Okay, it's okay that we don't understand what is a undirected, what is a graph, but I will show some visualized components that show they are connected to indicate the case. Okay, so within this connected components procedure of the graph G, what we're gonna call is the make set. Remember, the make set is that we create a new set that has just one element out of these input elements, okay? And then we will use another for loop to run this if statements iteratively. So this if statement compares whether the set that contains U and the set that contains V are the same set. Okay, so this find set on U will return the set that contains U, and the find set on V will contain the set that returns V, and we basically compare whether they are the same set. If so, if they are not the same set, we will union the 2 sets. Okay, so it's a quite straightforward algorithm, right? So let's see the results of it. Okay, let's see, we have a bunch of a graph that has 4 connected components. Okay, so these connected components can be identified by calling this procedure. So initially, all the individual all the vertices are initialized to the individual sets that contains only one element in it. So these sets, they are disjoint sets, okay? And then we're gonna take one edge out, and then we will run this if statement, right? we will examine whether the two vertices on the two ends of the edge, they belong to the same set or not, okay? So after the edge BD, okay, BD is right here. After BD is taken, we will examine whether B and D, they belong to the same set. And actually, indeed, they don't belong to the same set, so they will be unioned together, okay? So we create some new set, B, that includes B and D, okay? All right, and the next edge would be E and G. So E and G is taken, so the two nodes, two vertices E and G will also be unioned, okay? The next one is H and I. H and I will be unioned again. A and C and the HI, right? And then A and B is taken. Then they will, the two sets that contains A and the B respectively will be unioned, okay? And the E and F will be unioned. And lastly, when B and C is taken, then, okay, so we should pay attention to this step. After B and C is taken, because they are already in the same set, so nothing will be done in this step, okay? So after this last step is done, we will have four sets remaining in the collection, which is the 4 connected components, okay? Which means these 4 components, they are kind of isolated towards each other. There's no connection between these two, okay? All right, so that is a typical example of how disjoint sets are used in the connected components algorithm. And this connected components algorithm will be part of a more advanced algorithm in the future that we're gonna talk about in graph data structure. Okay, so I think this is the last slide for today. Yeah, so we are done with this data structure chapter, and hopefully it gives you a pretty good review of the fundamental, some of the fundamental data, basic data structures. Okay, so I will release the assignments and the quiz questions later today. Okay, the assignments maybe comes out tomorrow. Okay, I need to spend some more time on the questions. Okay, so yeah, that's pretty much for today. Any questions, you can raise it now, or you can let me know by email.